Hello, can you hear me?
Yes, sir.
How many people are here? Hello, can you see the board?
Yes, sir. We can see the board.
Okay. So we were doing this coefficient permanently.
Sir, we cannot see the entire board.
Okay, so let me adjust. Can you see now?
No. Oh, okay, sir. Now we can see. No, gone again.
Can you see now?
Okay, now we can see, sir.
Okay. So coefficient permanent B. Okay, so in coefficient permanent B, what we seen that definition that coefficient permanent B is the maximum value of semicircular deviation, deviation due to which varies the sign of course and is caused by Fourier horizontal component of ship's permanent magnetic field acting at the compass position. The cause was Fourier horizontal field. Fourier horizontal component of the ship's permanent magnetic field acting at the compass position, but in short, it was force P. After that, what we saw that how the deviation was changing with the change of force. So then we found that deviation due to PB, deviation due to coefficient permanent B, we find out directly proportional to sine of compass code. So this is what we did in the last class. Okay, so change in deviation due to change of force we have seen. Now the next thing what we'll see is the change in deviation due to change of place. If we change the deviation, sorry, what if we change the place? Okay, so when we say talking about the change of place, we are basically talking about the change of latitude. Okay, so when we are talking about the change in deviation due to change of course, that time we had kept the place same and we changed the vessel's course and we found that it is exactly proportional to sine of course. Now what we will do, we will keep the course same. Okay, but we will change the place and we'll see that what will be the effect of change of place on the deviation caused by coefficient permanent B, keeping the course same. Let us say place 1. So we can choose any heading. So let us say vessel is heading. We have choose the vessel heading as easterly. And what P the vessel is having, let us say vessel is having plus P. And here the value of H is equal to H1. Okay, it is the horizontal component of the Earth's magnetic field. That value is H1 at place 1. So if we draw this diagram, what diagram will get? We'll get this. And P is acting in this direction. H is acting in this direction. So this we have done it again and again. So this will be the resultant and this will be the deviation. So if I show this in the larger diagram here, so this is the compass position, this dot. This is that force P. And this is the value of H1. So this is what? This is H1 and this is force P. So the same thing we are showing it here separately. So this is H1, this vector is H1 and this vector is P. So what will happen? We draw the resultant. Let us say the resultant is acting in this direction. Okay. So if this force P was not there, your magnetic compass would have been needle would have been pointing in this direction. But now it is pointing in this direction. So basically what it is, this is the deviation. Okay. So this is the deviation what the vessel will observe at place 1, where the force P is this much and value of H is H1. Now we go to place 2. When we go to the place 2, what is the thing which is changing? The value of H will change. So as we go to the higher latitude, the value of H becomes less and less. Maximum at equator, cos H is equal to, you remember, F cos theta. And value of equator, value of theta at equator is 0. So cos 0 is 1. And value of theta at poles is 90. So H is 0. So as we go from the equator toward the pole, the value of H reduces. Let us say we go to place 2, where the value of H becomes half. Let's say H1 by 2. So we are keeping rest everything same, force same. With the change of place, will the value of force P change? Force P will remain same because it is a permanent force. It doesn't change. So this is remaining same, while this one will become half. So when this becomes half, let us say it is only up to here. It is only up to here. This becomes your H1 by 2, here to here. So now P is remaining same. So what will be the resultant? The resultant will become this. What will happen? Deviation will increase, right? So when this H becomes half, P remaining same. So the resultant will now acting in this direction. So your magnetic compass will be pointing in this direction. So obviously the deviation increases. If the vessel goes to a place where the value of H is increasing, if the vessel is going to the lower latitude, what will happen? Let us say value of H is now increasing. When the value of H increases, then your resultant will be going in this direction. So then your deviation will become this much. So with the increase in H, okay, value of deviation is reducing. And with the reduction in H, the value of deviation is increasing. So it is the same thing like let us say your ship is sailing in this direction and you have a beam current of 3 knots here. And your ship is going with a speed of, let us say, 16 knots. So your vessel will be deviated from the track this day. But if you reduce your speed from 16 knots, you reduce your speed from 16 knots to 8 knots, what will happen? And the current remaining same. Will your angular deviation from the track will increase? Yes, it will increase. So that is the same analogy we can give. So what we are having, what we have seen that with the increase in H, the deviation is reducing. And with the reduction in H, the deviation is increasing. So what conclusion we can write? That deviation due to coefficient permanent V is inversely proportional to H. Inversely proportional to H. So H is increasing, deviation is reducing. H is reducing, deviation is increasing. Understood? And with the change of place, what is the other thing which will change? Z will change. Is the Z playing any role here? Answer is no. Only H is changing. H is having a role here. Z will not have any effect on the deviation caused by coefficient permanent V. Is it clear? Hello?
Yes, sir.
Yes, sir.
Next thing is that how do we calculate coefficient permanent V? because before we think of correcting, okay, before that we have to think about that how much is the deviation. So as I said that we cannot calculate force P, but what we can calculate is the deviation caused by force P, and then we can correct that then we can correct that coefficient caused by force P. So if we correct the deviation caused by force P, that means the force P will also get corrected. So now what we are going to look at calculation. Can you calculate PB? No, we cannot calculate PB. What we can calculate is only the total value of B. And the total value of coefficient B is the sum of permanent B and induced B, where the induced B is a relatively much smaller component compared to permanent B. But what we can calculate is only the value of coefficient B. We cannot calculate the individual values of PB and IB. Then how it is done? Because the value of IB is small, so IB is corrected by estimation. Let us say your total coefficient B is equal to PB plus IB. And let us say IB I correct and IB I make it 0. So if IB I make it 0, then coefficient B will be equal to PB only. So what we do is that we correct the IB by estimation and we make it 0. So when this one is corrected, then coefficient B is equal to PB. But that is how practically it is done also on the ship. So how do we calculate coefficient B? Okay, or in the bracket I am writing basically if IB has been corrected, then coefficient B will be equal to PB only. So what is the formula for that? Deviation on east minus deviation on west divided by very simple formula. Deviation on east minus deviation on west divided by 2. That will give you the value of P, or that will give you the value of B. So what is this total deviation on east minus deviation on west? This is the total deviation. Total deviation obtained on easterly heading and total deviation obtained on westerly heading. So this is the deviation due to all the coefficients. This is the deviation due to all coefficients. So how will I come to know what is the deviation on east? What we can do is that we can head the vessel easterly direction, and then we can take the magnetic compass bearing of star, or let us say magnetic compass bearing of sun, and we can calculate the true bearing of the sun. So that the difference will give us the compass error, and to that compass error we can apply the variation. So we'll come to know the deviation on east. So this deviation on east will be total deviation caused by everything, all the components or all coefficients. Same thing we can repeat for when the vessel is heading in the westerly direction. Okay, so then this total deviation on east minus total deviation on west divided by 2 will give you the value of coefficient B. Okay, so from where this formula has come, so let us look at briefly at this. Let us say yesterday I have shown you that how it is shown. What is the quick way of showing that change in deviation due to change of vessel heading? So for coefficient B, we are shown like this. Coefficient B, we are shown like this. So this line where it is cutting the circle, on those two headings, the deviation is 0. So this is your 0, 0, 0, and this is 180, and this is of course 0, 90 and 27. This was easterly and this was westerly. This is my coefficient B. Similarly, as you will see in the future, okay, this will be for coefficient C. This one will be east and this is west. And all of them I am drawing it for plus B. This is plus B, this is plus C. This is coefficient C. So coefficient deviation due to coefficient C, as you can see, is 0 on easterly heading and 0 on westerly heading. And here it is easterly, here it is westerly. Then we can draw for coefficient D. Coefficient D, the deviation is 0 on these 4 headings. Northerly heading, easterly heading, southerly heading, and westerly heading, the deviation is 0. And here it is east, west, east, and west. And lastly, the coefficient E. Coefficient E is like this. So the deviation due to coefficient E is 0 on 4 headings: northeast, southeast, southwest, northwest. So on these 4 headings, the deviation is 0. And then we can write here east, this is west, this is east, and this is west. Okay. So this deviation, what we see here, it is due to all this B, C, D, and E. So can you see that this total deviation on east, is it having any component coming from coefficient C?
No, sir.
Okay, because on easterly and westerly heading, the deviation due to coefficient C is 0. That means that means the coefficient C is not involved here. Okay, is coefficient D is having a component here?
Yes, sir.
How? On easterly and westerly heading, what is the deviation due to coefficient D?
Okay, sir. No, sir.
Okay, so this is easterly heading, this is westerly heading, this is easterly heading, this is westerly heading. So the deviation due to coefficient C is 0 on these 2 headings, and deviation due to coefficient D is also 0 in these 2 headings. That means this one is having coefficient deviation not due to C and D. That means here the total deviation, what we are saying, it is only due to B and E.
Yes, sir.
Hello?
Yes, sir.
Okay. So now you can see here, okay, what I have written here, westerly. So let us say if the deviation due to coefficient E is, let us say, 4 degrees east here. Sorry, 4 degree west here, because this is everywhere it is west. So how much it will be here? Here also it will be 4 degree west. By symmetry, because it is all symmetrical about x-axis. So if the deviation on easterly heading is 4 degree west, then the deviation on westerly heading will also be 4 degree west. So whatever is the component of coefficient D, will that get cancelled, because in between you are having a negative sign. So 4 degree west minus 4 degree west, that will become 0. Hello.
Yes, sir.
So will will the component due to coefficient D will get cancelled when we put in this formula? Because there is a negative sign in between.
Yes, sir.
And what will happen to the component due to coefficient B? Here what we do is that in this formula we put easterly deviation as plus and westerly deviation as minus. So if we put this minus 4, so this will be minus 4 minus 4, and ये वाला minus is this here, minus 4. So this will become minus 4 plus 4. So this will, so what will happen to deviation due to coefficient B? Let us say here it is 9 degrees east. So if the deviation on easterly heading is 9 degrees east, then what is the value of coefficient permanent B? If the deviation on easterly heading is 9 degrees east, then what is the value of coefficient permanent B? I'm repeating again. Suppose the deviation due to coefficient B is 9 degree east on easterly heading. Then what is the value of coefficient B? What is coefficient? Coefficient is what? Maximum value of deviation. What is
Yes, sir.
coefficient? Maximum value of deviation. And here the maximum value of deviation will occur in what heading? In which heading?
90 degrees.
Okay. The maximum deviation will occur on easterly heading. And what is the deviation you are getting in easterly heading? 90 degrees.
9 degrees east.
So can we say that coefficient B will be equal to +9?
Yes, sir.
I repeat again, what is coefficient? Coefficient is nothing but maximum value of deviation. Okay. And due to coefficient B, okay, which is actually caused by force P if you talk about PB. Okay. So the maximum deviation will occur on easterly and westerly heading. So what is the deviation we are getting on easterly deviation on easterly heading 9 degrees? So this is the maximum value of deviation. And what is coefficient? Coefficient is nothing but maximum value of deviation. In this case, what will be coefficient B? +9, right? Because on easterly heading, on a heading just to the north of east, what we are getting here, easterly. So it is coefficient B is equal to +9. Okay. But this we don't know. And do we know this? No, we don't know this. This though I have for the teaching purpose I have written. When we do the observation, when we find out the compass error using some let us say sun or star or using some terrestrial object, what we come to know is the total deviation caused by all the coefficients. So if here it is 9 degree west, then here it will be how much? 9 degree. So if here it is 9 degree east, so here it will be 9 degree west.
Yes, sir.
So we have seen in the deviation due to change of course. So it is symmetric. So what will be the total deviation on easterly heading? If one ship is having like this, so what will be the total deviation on easterly heading? This is 0, this is nil, this is nil on easterly and westerly heading. Here it is 0, 0. Okay, 0, 0. Here everywhere it is 0. So what will be the total deviation on easterly heading on this ship?
Coefficient B and E.
So what will be the value?
13 degrees.
Huh? 13 degrees or 5 degrees? This is 9 degree east, na? And this is how much?
4 degrees west.
So how much you will have? Total deviation will be how much?
5 degrees.
5 degrees. So when we take the compass error using sun on this shape, what is the deviation on easterly heading you will get? 5 degrees, correct? So we put here 5. Easterly we are putting as what will be the deviation on westerly heading?
Oh. Division westerly heading. (14 degrees west).
Okay, here it is 4 degree west, and here it is 9 degree west, and here it is 0, here it is 0. So the total deviation on westerly heading will be 13 degree west. Okay, so the deviation on east here you will get total deviation is equal to 5 degrees east, and the deviation on westerly heading will be 9 degree west. So this is the value which I will get when I do it using the sun. When I take the compass bearing of the sun, we calculate the true bearing of the sun, then we apply the variation. So this is the value of deviation we will get. So if I put these values of deviation on this formula, what we get? So easterly we are putting as plus and westerly we are putting as minus. 5 degree minus 9 divided by 2. What you will get?
7 degrees.
Okay, just a minute, let me see. 4 degree west plus 9 degrees kitna hua? 5 degrees east. And 4 plus, sorry, it will be 13 degrees. 13 degrees west. Okay, 4 degree west plus 9 degree west will be 13, na? 13 degrees. So this will be minus 13. What you will get?
9 degrees, sir.
Plus 9. So that is what we should have got. Correct? That is what we should have got. So actually what happens that this component will get cancelled. इसको आप ऐसे लिख सकते हैं. This component will get cancelled. So 5 degree west को आप ऐसे भी लिख सकते हो. Okay, this is 4 degree west. And then 4 degree west, this one. Okay. And then plus 9 degrees east. Okay. Minus. यहाँ पे क्या हो गया? इस वाली हेडिंग पे 4 degree west. और यहाँ पे क्या हो गया? 9 degree west. ठीक. तो अभी देखो 4 डिग्री वेस्ट और ये 4 डिग्री वेस्ट कैंसिल हो जाएगा. ठीक. 4 degree west and 4 degrees west will get cancelled. So what you will have 9 degrees east and 9 degree west here. So 9 and west we are putting as minus. So 9 minus minus 9. So because this component will get added up. Okay. This component will get added up and this component will get cancelled out. So because this component is getting added up, that is why in the denominator we are having 2. So what we get? Plus 9. Right? So that is how we calculate the value of PV. Understood?
Yes, sir.
By using this formula, we can, and this is how practically also the value of coefficient B, because IB has been corrected previously by estimation. So whatever will get from the coefficient B, that will be the value of PV only. So once we get to the value of PV, then the next thing will be correction of PV. How do we correct PV? Let us say PB का value, corrected value we got as PB is equal to plus 9. Plus 9 means, is it being caused by force plus P or minus P? So we have seen it yesterday. If it is plus PB, that means the vessel is having plus P. Plus P means there is a force acting towards top. So now I have to correct this force. But I don't know the value of the force, but I know that it is causing 9 degree deviation when the vessel is heading easterly or westerly. What we do? Let's say this is the shape. Okay. This is the accommodation. This is, let us say, magnetic compass binnacle, and this is the position of the magnetic compass, and this is the binnacle. So we zoom this part, zoom, and we show it separately. So this is the forward part, and this is the aft part. And here, because the PB is plus 9, we know that there is a force P acting in this direction. P is acting in this direction. So when we are zooming this part and showing it separately, this is the magnetic compass binnacle. This is the magnetic compass. And at the magnetic compass, we are having a force acting in this direction. So what is this force? This force is acting in the forward direction. This is a horizontal force, and this is a permanent force. This is a permanent force. This is acting in the horizontal plane, and this is acting towards forward. So now we have to correct. So in the magnetic compass correction, we use a term which is called like for like. Like for like. Okay. Or Hindi mein you can call it जैसे को तैसा. That means whatever is the cause, the same kind of correction is provided. So because it is a permanent force, we will correct it by a permanent magnet. Or it is a horizontal force, okay, we will do it by horizontal magnets, creating a horizontal field at the compass. And of course, because it is acting towards forward, so we will create an equal and opposite force acting towards up. So what we will do, we put the character magnets like this. So the below the magnet, we keep the 4.5 horizontal magnets. Okay. So what we can write here? So what are these? These are the 4.5 horizontal power magnets. So you can say coefficient permanent B is corrected by keeping 4.5 horizontal permanent magnets below the compass position. So coefficient permanent is corrected by keeping 4.5 horizontal permanent magnets below the compass. So what is this? This magnet is a permanent magnet. It is kept below the compass position and it is kept in the 4.5 direction and it is kept in the horizontal plane. Okay. So in this case, what we'll do, we'll keep the red end forward, keep the blue end down. So the force is going from red to blue, and this point will be somewhere in the center. Okay, of this line. So what will happen? The lines of forces which are going to the compass position will be going in this direction. So at the compass position, will due to this character magnets, you will have the force acting in this direction. This is the corrective force provided by this magnet. Now we can increase and decrease the amount of this force or amount of correcting force in three ways. Either I can keep a stronger magnet and weak magnet. That is one way. Second way is that I can increase and decrease the number of magnets. And the third way is that I can bring the magnet closer or we can take them away. If you want more correction, we can bring these magnets closer to the compass position. If you want less correction, then we can keep it away. So if any one of you have seen open the magnetic compass binnacle, okay, then you would have seen some magnets lying in the 4.5 direction below the compass within the binnacle. Has anybody seen? The magnets lying in the 4.5 direction?
Yes, sir, we have seen.
Okay, so that magnet what you have seen in the magnetic compass binnacle, that is to correct value of PB. Okay. Okay. So यहाँ पे we can complete this so as to correct the calculated value of PB. What was our calculated value of PB? Plus 9. So it will be corrected plus 9. Okay. If a vessel was having, let us say, minus PB, let us say PB was coming -7, and how will come to know PB is coming to -7? When we put in the values in that formula, PB is equal coefficient B is equal to deviation on east minus deviation on west divided by 2. So if that is coming out to be negative, so that itself will tell me that it is negative. In that case, what will happen? We keep the compass position and you are having minus P. So what we'll do, we'll keep the magnets, 4.5 horizontal permanent magnets. In this case, we'll keep the red end off and we'll keep the blue end forward. So now the lines of forces are going from this red to this blue like this. At the compass position, we'll have the force acting in this direction. So this corrective force what we are providing will be in this direction. So if the vessel is having plus PB, indicating that vessel is having plus P, then we'll keep the red end forward. And if the vessel is having minus PB, that means the vessel is having minus P, then we'll keep the red end forward aft. Is it clear?
Yes, sir.
So are we correcting force P or are we correcting the coefficient of 9 degrees? What we are correcting is coefficient, value of coefficient, which is 9. So that means we are correcting the maximum value of deviation. And maximum value of deviation will occur on which heading? In the case of coefficient comment B.
East and west heading.
So on which heading you should carry out this correction?
West heading.
Easterly or westerly, anything. So here we will add one more line while the vessel is heading easterly or westerly. Because you are correcting the maximum value of deviation, you are correct because you are correcting the coefficient, and coefficient is nothing but maximum value of deviation. So you have to correct it on a heading on which the maximum deviation will occur. In this case, maximum deviation will occur on which heading? Easterly or westerly. So your vessel should be heading easterly or westerly when you are placing these magnets, when you are carrying out this correction. Understood? So just to tell you briefly, okay, how practically it will be done. So now you have calculated the value of PB is equal to plus 9. And you know that magnet has to be kept in this position. And the vessel has to be heading easterly or westerly. Let us say I am choosing the heading easterly heading. So now what I will do, I will tell the AB to steer east by magnetic compass. So I will tell the AB that now you look at the magnetic compass and steer using the magnetic compass, so that you are maintaining east by magnetic compass. So when the vessel is steady on easterly course as per the magnetic compass, then I will note down the corresponding gyro heading. So that corresponding gyro heading could be 096 or it could be 084 or 083. After that, what I will do is that I will tell the AB that now you steer using the gyro compass. Okay. While on which gyro compass course, so as to maintain east by magnetic compass. Is this clear? So I tell the AB to steer by using the gyro compass so as to maintain east by magnetic compass. Because as soon as you keep this magnet, your magnetic compass is going to deflect. Then you will not be able to use the magnetic compass for steering. Okay. So now the vessel is heading east by magnetic compass. Now.
So can you please repeat? I did not understand.
Okay. So what you do is that you tell your AB to steer using the magnetic compass. So all of you would have done in your steering time, you would have done some part of steering in using the magnetic compass.
Yes, sir.
So you tell the AB to steer east by magnetic compass. Okay. So now your vessel is east on magnetic compass. So that time the gyro heading will be something else. It could be 083 or it could be 098 or something, whatever. So then you note down the corresponding gyro heading. After that, you tell the AB to steer using that corresponding gyro heading. So if you are using that corresponding gyro heading, will you be maintaining east by magnetic compass?
Yes, sir.
Okay, so that is what we are doing. After that, what you do that this vessel is having PB is equal to plus 9. Okay. So on a easterly heading, this PB is equal to plus 9, how much deviation it is causing? Because the vessel is having PB is equal to plus 9. So on easterly heading, how much deviation this is causing? 9 degrees east, correct?
Yes, sir.
So this coefficient P, how much deviation it is causing? 9 degrees east.
Yes, sir.
So how much this character magnet should cause?
9 degrees west.
So as soon as now you can see that in this case you can see that this force is acting towards aft in this case, and this force is acting towards forward. So let us say this is forward and this is aft. Okay, this means this is forward, this is aft. This force is acting towards aft. So now at the magnetic compass position, you have this force P, okay, which is causing this 9 degrees east. So at the magnetic compass, we are providing this corrective force. Corrective force, let me show it by blue pen. So this corrective force, this is your corrective force. Corrective force which is being provided by this one. This is the corrective force. So how much the corrective force should cause? Corrective force should cause 9 degree west. Correct? In order to nullify the force P, because the force P on this heading is causing 9 degree east. So how much this character magnet should cause? 9 degree west.
Yes, sir.
So you can see your H is pointing in this direction. So as soon as you keep this magnet, this force will start acting in this direction. So will your magnetic compass deflect? When you
Yes.
keep this magnet, this force starts acting in this direction. That means in this direction. Will your magnetic compass deflect?
Yes, sir.
So we knew the magnetic compass reading or magnetic compass course before keeping these magnets. And now what we do is that we achieve 9 degree west deflection with the help of these magnets. So we adjust the magnet, we keep the sufficient number of magnets, then we adjust the position of the magnet in such a way so that with the help of this magnet, we achieve 9 degree west deflection of the magnetic compass. Understood?
Yes, sir.
So once we have achieved 9 degree west deflection using this one, that means these magnets are causing 9 degree west, while coefficient this force P was causing 9 degrees. That means have we nullified this force P? This one was causing 9 degree east, and this force is causing 9 degree west. That means we have provided equal and opposite force to force P.
Yes, sir.
So that is how the correction is done. So once the force P has been nullified, once and for all, so this deviation, this correction will hold good for all the places and for all the headings. Because once force P is not there, then the coefficient permanent B has been totally nullified. Okay, has been made 0. So then on any heading or at any place, the deviation due to coefficient permanent B will be 0, or the deviation provided by this force P will become 0 because the force P has been nullified.
Excuse me, sir.
Yes.
So, but the magnets that we are keeping, how do we know how much, how many magnets to keep over there?
No, what we do is that we keep these magnets and then we adjust the magnets, okay, and number of magnets because you have the slots being provided. So you keep the in the slots, okay, and then you keep the sufficient some magnets, and then you see that whether you are achieving this 90 degree west deflection or not. If you are not achieving, then you keep more magnets. Still you are not achieving, so you bring them closer. So यहाँ पे let us say in the magnetic compass binnacle you have the slots. Let us say now you are looking at the magnetic compass binnacle. How do we show? So let me show in the end view. So let me show the end. So you are looking at the magnetic compass binnacle from aft. So these are the slots. Let's say these are the slots for the 4.5 magnets. तो यहाँ पे मैंने मैग्नेट डाला और यहाँ पे मैग्नेट डाला, कुछ नहीं हुआ. फिर यहाँ पे भी डाला, यहाँ पे भी डाला, तब भी हमारा पहले हमने यहाँ पे डाला, यहाँ पे डाला, यहाँ पे डाला और यहाँ पे डाला, नहीं हुआ. What I should do? This was giving only the correction of, let us say, 9 degrees, or sorry, 5 degrees west. So then I brought them here. Okay, we took out the magnets from here and we put them here. So then here we got, let us say, 9 degree west deflection. So we leave them there. Understand? Hello.
Yes, sir.
So if we want more correction, if by keeping the magnets in the lower slots, if the correction provided is less, then we will bring them into the closer slots. And thereby, same way we can increase and decrease the number of magnets also. Let us say, in this case, let us say it is giving 11 degrees. So what we do is that we remove these two magnets. Then we see that it is coming closer to 9 degrees. Okay.
Yes, sir.
So this is how the correction is done. So once the coefficient permanent B is corrected, it is corrected for all the place, for all the forces and for all the places. Okay. So once the coefficient permanent B has been corrected properly, let us say it has been corrected properly, then there will be no deviation due to coefficient permanent B at any place or on any force. Okay. So let us say when the vessel goes on easterly heading, the force P is acting in this direction, so it is not providing any deviation. So this corrective force is also acting in this direction. This is also not providing any correction. Understood?
Move the camera a little, sir. We cannot see the left side of the board.
Can you see now?
Sir, a little more, please.
Okay,
Yes, now we can see. Yes, sir.
So what I am saying that when the vessel goes on northerly heading, so this force P is not providing any correction. So now the corrective force is acting in this direction. So this is also not providing any deviation. If the vessel goes on this heading, okay, force P is acting in this direction and this force is acting in this direction. So basically, once the force P has been nullified, then there will be no deviation on any heading, and there will be no deviation when you have a change of place also. Okay.
Yes,
Hello.
sir. Yes, sir.
Okay, so that completes this coefficient permanent B. Which exam you had today? You had exam today, no? Which exam?
Sir, maritime legislation.
Long time back I used to teach, but now I teach in ASN. Similar topics. Okay, so the next coefficient will be coefficient induced B. As the name suggests, I induce B. So as the name suggests, it is caused due to what, soft ion magnetism or induced magnetism. So what is the definition of induced B? So the coefficient induced B is the maximum value of semicircular deviation, which varies as sine of course. So first half of the definition of coefficient permanent B will be same. Okay. So coefficient IB is the maximum value of semicircular deviation. This is the sign for deviation. The deviation due to which varies as sine of course. So up till here, the coefficient, the definition of permanently induced B is same, and is caused by here. From here, the change is happening, and is caused by fore and aft horizontal field, fore and aft acting at compass position to induced magnetism in vertical soft iron located forward or aft of compass position. The coefficient induced B is the maximum value of semicircular deviation. So what is semicircular deviation? That you have already seen. Deviation due to which varies the sign of course. So that you have seen in the case of PB. Okay. In this case also we'll see. And it is caused by fore and aft horizontal field at the compass position due to induced magnetism in the vertical soft iron, which is located forward or aft of the compass position. So what will be this like this? Let us say this is the shape. Okay, so obviously this is forward and this is aft. Let us say this is accommodation and monkey island. Let us say you have the magnetic compass position, and behind that we have the funnel. And for the sake of simplicity, let us take the top of the funnel is in the same horizontal plane as the magnetic compass. If it is above or below, that doesn't matter. Will cause the same effect. So maximum amount of IV on the shape is caused by funnel. And funnel is the biggest piece of vertical soft iron on the ship. And also the top of the funnel is more or less in the same horizontal plane as the magnetic compass. Even if it is above and below, it doesn't matter. Okay. So what will happen? That let us say this is a soft iron. This is vertical soft iron. So vertical soft iron will receive induction from Z, which is the vertical component of the Earth's magnetic field. So Z is acting in this direction, vertically downward. Let us say we are discussing northern hemisphere. So because Z is acting in this direction, so obviously the side from where it is entering, that will become blue, and will become blue. And what about the other end? That will become red. This becomes blue and this becomes red. So because this one is far away from the compass position and this is closer, so let us say we ignore this. Because as you know that distance, the field is in approximately inversely proportional to the cube of the distance. Okay, so let us say ignore this. So then what will happen? Below the after the compass position, we have a blue pole. And the compass we always treat it as a red. So let us say if we show the same thing on the plan view, let us say vessel is heading in the easterly direction. So the course of the vessel is easterly. Here also easterly. So we have the compass position here, and behind the compass we have a blue pole. Okay. So the compass, you treat it as a red, then what will happen? Due to that, there is a force acting in the half direction. So due to this blue pole and the magnetic compass, the force acting in this direction. In which direction H is acting? H is acting in this direction. So again, what this force will do? This force will deflect the magnetic compass. So you will have westerly deviation. So that is what is the IP. You can see. So this force here, you can show it like this. So this is, you can say, it is acting in the half direction. It is in the horizontal plane. Okay. So that is why 4.5 horizontal field. So in this case, it is aft. In some other cases, let us say if I take the vertical shaft and forward, then the force will become forward in the forward direction. So it's caused by 4.5 horizontal field at the compass position, 4.5 horizontal field at the compass position due to induced magnetism in the vertical software. So due to induced magnetism in this vertical software. So this is the funnel is the vertical software. So induced magnetism in the funnel. Because of that, there is a force acting in the 4.5 direction. Even if this compass is, let us say, located here, slightly below, then what will happen? This will become blue. So because of that, the force will be acting in this direction. So of course, it will have a horizontal component. This horizontal component, what it will do? It will cause IP. Okay. So even if this force is acting in some oblique direction like this or this, it will have a horizontal component. But for our illustration, we will take the top of the funnel always in the same plane. Okay. So I think that is sufficient for us today. We'll continue in the next class. Okay.
Okay, sir. Thank you.
Camera close.